Hello! Last time, we proved Myerson's lemma when the allocation rule x is piecewise constant. We derived a unique payment rule such that it is DSIC. Recall that the payment rule can also be interpreted as the area to the left of our bid on the graph for the allocation rule. We now apply the payment rule to the single item auction and the sponsored search auction. We start with the single item auction. Let X be the allocation rule that gives the item to the highest bidder, with a consistent tie-breaking rule. This is a monotone allocation. We consider a player I and the bids B minus I from the other players. We let capital B be the maximum bid from the other players. So what does the allocation function look like for player I? We need to look at how much does a player get depending on what bids they give. We see that when a player bids B or less, they get 0. If they bid more than B, then they are the highest bidder, so they will get the item and the allocation is 1. Now, what happens for the function at B, whether the allocation is 0 or 1, is dependent on the tie-breaking rule, but it will not affect our analysis. So the allocation function has one jump at z equals to b, and the jump height is 1. When the bid bi is greater than b, player I wins, and the payment is the area to the left, which is b times 1, and that is b. And this is precisely the second price rule. Based on Myerson's lemma, it is the unique payment rule that is DSIC. Assuming that the bid is 0 implies that the payment is 0. So the second price rule is the unique ideal auction in the case of the single item auction. Now let's look at the sponsored search auction. Recall that in the sponsored search auction, we had k slots up for grabs with click-through rates alpha 1, alpha 2 all the way down to alpha k in that order. Our allocation function x assigns alpha j to the jth highest bidder. This is a monotone allocation function, and you can check that. So we can apply Myerson's lemma to get the payment rule that is DSIC. We now calculate what is the appropriate payment for a player if they win some parts of this auction. Let's consider a player I and the bids B minus I for the rest of the players. We will assume that the k highest bids other than BI is B1 to BK in that order. We will ignore the remaining bids. So, what does the allocation graph look like for player I? Well, player I gets alpha k if their bid is between bk and bk minus 1. They get alpha k minus 1 if their bid is between bk minus 1 and bk minus 2, etc. So the allocation rule has jumps at bk, bk minus 1, bk minus 2, etc. And the height of each jump is alpha j minus 1 minus alpha j. So using the formula, the payment for player I if they bid Z is the sum over all the jumps before their bid, the jump location bj times the height of the jump alpha j minus alpha j plus 1. We will assume that alpha k plus 1 is 0. And this payment is represented by this green area here. And this is the unique DSIC payment rule. Let's have a look at our previous example where we had 2 slots with CTR 0.7 and 0.5, and the 3 bidders have the bids 10, 9, and 2. Our allocation rule will give 0.7 to player 1 and 0.5 to player 2. But can you figure out the correct payment for each of them? Try to draw the allocation graph for each player assuming truthful bidding from the other players, and then try to figure out what the payment should be. For player 1, there are 2 jumps at 2 and 9. If they bid less than 2, they get 0. If they bid between 2 and 9, they will get 0.5. And if they bid more than 9, they will get 0.7. If player 1 also bids truthfully at 10, then their payment here is 2 times 0.5, this is before the first jump, plus 9 times 0.2, that is before the second jump. So the total payment is 2.8. The allocation for player 2 looks similar, except the jump points are at 2 and 10. The payment this time has only one segment, and that is 2 times 0.5, which is 1. And we have applied Myerson's lemma to our 2 auctions in this course. In the next lecture, we will look at another example of an auction. This time, we will know for sure that it is impossible to be ideal. But we will still make sure that we get somewhat close to ideal.